Hi friends, this is Nagajyoti working as an assistant professor in Department of an ECE. So, in this session, let us discuss the applications of an op-amp. So, in the last session, we have discussed the basic operations which will be performed by an op-amp. That is how the op-amp can be used as an adder or a subtractor or adder and subtractor. In this, along with the basic operations, we know that op-amp can also be used to perform different mathematical operations such as integration, differentiation. So, let us start our topic with how op-amp can be used as a differentiator circuit. So we know that the op-amp should be connected in the closed loop gain, whether towards the inverting or a non-inverting mode. But in order to improve the utility of an op-amp, we need to connect a negative feedback path to an op-amp. That is the reason for all the circuits we are feeding back the outputs towards the input to the negative terminal. So, what is meant by a differentiator? A differentiator is a circuit which performs mathematical operation of differentiation. That is, output voltage should be derivative of the input voltage. And if we observe the circuit of this differentiator, the input is given to an inverting amplifier through a capacitance and output is taken across a resistance. So, in simple words, we can say that here a differentiator is nothing but an high pass filter which allows higher frequency components to pass but rejects lower frequency components. So, from the same circuit, we must be able to justify how output is derivative of the input, as well as how can we say it rejects the lower frequency components. So here, in order to prove output is derivative of the input, we need to apply the nodal equation at the inverting input terminal. So here, according to the virtual ground concept, the voltage across the inverting terminal is equivalent to 0 because the voltage at non-inverting terminal equal to 0. And we can write down the current flowing through a capacitance is equivalent to capacitance into derivative of the difference of the voltages. So here the current flowing through the capacitor C is equivalent to d by dt of input voltage minus 0 itself indicates virtual ground concept. Similarly, the output voltage is equivalent to minus V0 into R. So if we simplify this, we'll be getting V0 is equivalent to minus RC dVi by dt. Here 0 represents a voltage because of virtual ground concept. So here the output is a derivative of the input signal if we are assuming the RC values is equivalent to 1. This is how we can say that output is derivative of the input. And in case of an output expression, we are having a negative sign. The negative sign represents there is a phase shift between the output and input waveforms. And if we want to prove how the op-amp can be used to reject low frequency components and to pass high frequency components, we need to write down this output voltage in terms of phasor equivalence. That is, by using a Laplace transform, we need to represent this complete time domain equation into S domain or a Laplace domain equation, and we need to replace S is equivalent to j omega. Then we need to calculate the gain. We know that gain is nothing but output voltage by input voltage. So from that we can say that we'll be getting a frequency f is equivalent to 1 by 2 pi rf c1. So we can represent gain equal to f by fa. If f and fa values are same, then gain is equivalent to 1, or gain in dB is equivalent to 20 dB per decade. If f is greater than fa, that is for higher frequencies, the capacitance is going to be unstable and breaks into oscillations. So the input impedance is going to be decreased with increase of frequency. Thereby it is making a circuit more sensitive to higher frequencies. So in order to avoid this, instead of using a simple differentiator circuit, we need to use a practical differentiator circuit. And the difference between this differentiator and a practical differentiator is, along with input capacitance C, we need to add other more resistance. Similarly, along with the feedback resistance, we need to add a parallel capacitance so that we can reduce the sensitivity of a differentiator circuit. And these are the some basic input and output waveforms of a differentiator. So here we are assuming that the first type of the input signal which we are applying is a square wave. So if we differentiate a square wave, we'll be getting output as spikes. Means we'll be getting only a part of a signal and the remaining signal is going to be striked off. Similarly, if the input is a triangular wave, output is a square wave or a rectangular wave depending upon the slope of a triangular wave. And the last is, if the input is a sine wave, differentiation of a sine as a cosine. And these are the waveforms in which they are assuming that they didn't specify here the negative value, only they have specified it as positive. But if we do it in the practicals, we'll be getting the output as inverse, that is 180 degrees phase shift with that of input. This is all about a differentiator circuit and its corresponding waveforms. And the next application of an op-amp is an integrator. So here a circuit which will perform the operation of an integration is called as an integrator. So here we need to prove the output voltage is equivalent to integral of the input voltage. And if we observe the circuit diagram, the only difference between a differentiator circuit and integrator circuit is here the input is given across resistance and output is taken across a capacitance. That is, if we interchange the resistance and capacitance of a differentiator, then such a circuit is called as an integrator. So here we need to apply the first KCL at that particular node. So here the voltage at a node VA is equivalent to, according to the KCL, the incoming current should be is equivalent to outgoing currents. So at VA, the incoming current one is I1, that is input current. Similarly, there is other more current, feedback current, which is getting into a VA. So I1 plus IF is equivalent to I minus. So here minus represents the input it is applying towards the inverting terminal. But we know that the ideal op amp will not take any current into the op amp. That is the reason this I minus value should be equivalent to 0. Therefore, the expression can be written as I1 plus IF equal to 0. So, from that we can say that I1 is equivalent to minus IF. So, we know that I is nothing but V by R. Similarly, here I1 is nothing but input voltage minus voltage across the node, that is VA. V in minus VA by R, and IF is nothing but feedback current. So the current flowing through the capacitance is written as C into dV by dt. So the output voltage is output voltage minus voltage across node A. But according to the virtual ground concept, VA value should be equivalent to 0 because the positive terminal of an op amp is equivalent to 0. So if we substitute the value of VA equal to 0, we'll be getting V in by R equal to minus C dV naught by dt. And if we are integrating with respect to t on both the sides, we'll be getting an expression in terms of output voltage in input. That is, output is minus 1 by RC integral of input voltage. Here minus 1 by RC, minus represents there is 180 degrees phase shift between input and output, and 1 by RC value is a magnitude or an amplitude of an output voltage. So here, depending upon R and C values, we can know that what must be the amplitude of the corresponding output voltage. So here the integrator can also be used as a low pass filter, means the same circuit is used to allow low frequency components and to reject high frequency components. In order to prove it as a low pass filter, we need to apply Laplace transform, that is, we need to write down gain in terms of j omega, and from that we can prove how the integrator acts as a low pass filter. Now let us see what are the input and output waveforms of an integrator. So if we are applying the input for an integrator is a step waveform, the output, that is, a step waveform is nothing but in which after some instant of t, that is t greater than or equal to 0, will be having constant amplitude. So if we integrate the constant amplitude, we'll be getting the output as a negative going ramp, and the slope of this negative going ramp depends upon the value of t. Similarly, if we apply the input as a square wave, the output which we are getting will be a triangular wave. If the input is a sine wave, the output is a cosine wave. So if we observe all these, if the input is at the positive, the output will be in the negative. If the input is negative, output is in the positive. That itself indicates there is 180 degrees phase shift between input and output because we are giving the op amp to the inverting terminal. So the next application of an op amp is how to use an op amp as a comparator. So here the name itself indicates it is a circuit which is used in order to perform the comparison operation. So if you remember, in case of the op amp as a differentiator, that is op amp as a differential circuit, we are giving input to both the terminals. So here also, similar to the subtractor circuit, we need to give the input to both the terminals of an op amp. And the other more interesting thing in case of a comparator is whatever the things which we have seen till now, in all those cases, the op amp is used in a closed loop gain, that is with a feedback path. But if we observe this circuit, the op amp is used in an open loop configuration, and the output in an open loop configuration varies in a non-linear manner, that is either two values either towards a plus V saturation or towards a minus V saturation. So in case of a comparator, we are giving for one of the terminals as input signal and other terminal is given with some reference voltage. So if we observe this circuit, the input is given towards a inverting terminal and reference voltage or a threshold voltage is given towards a non-inverting. So for whichever terminal we are giving input, we need to say that as a type of a comparator. That is the reason we are calling this as inverting comparator. So it is comparing the input voltage with the reference voltage or a threshold voltage. So depending upon these, the comparators may be either inverting or non-inverting. So this is inverting comparator in which the input is given towards a inverting terminal. So here output voltage will be only two values, that is plus V saturation or minus V saturation. So whenever input voltage is less than the reference voltage, when input voltage is less than the reference voltage, actually we need to get output voltage should be lesser value, but as we are connecting in an inverting mode, instead of getting minus V saturation, we'll be getting plus V saturation. Similarly, when input voltage is greater than V saturation, output which we are getting will be lesser value. That is just the reverse operation for the original value. So here if we observe the output waveforms of a comparator, the input waveform which we are giving is a sine wave, but the output waveform which we are getting is a similar to that of the square wave. So here a comparator will convert a sine wave or continuous wave into a two-level discrete values, whether it may be a rectangular wave or a square wave. This is the structure of a non-inverting amplifier. So as the name itself says that the input should be applied towards a positive terminal and the negative terminal should be connected towards a reference voltage. So here whenever input is greater than V reference, the output will be plus V saturation. When input is less than V reference, output will be minus V saturation. So if input is greater, we'll be getting positive value. If input is lesser, we'll be getting negative value. But whereas in case of an inverting, it is a just reverse process. So these are the waveforms of a comparator circuit. The input is a sine wave, and here for the first figure we are assuming that the reference voltage is a positive reference. So depending upon input which we are giving and the type of reference which we are giving, the comparators may be inverting comparator, non-inverting comparator with positive reference, as well as the same thing with negative reference. So here the dotted line represents that intersection of reference voltage with that of the input voltage. Whenever both input voltage is equivalent to reference voltage, the output will be a zero value. So here when input is greater than the reference voltage, output value is equivalent to 0. That itself says that it is a waveform for inverting comparator. Similarly, if we observe the second figure, instead of giving it as positive reference, here we have given it as negative reference. So in this, input voltage is greater than reference voltage, but the output which we are getting is minus V saturation. So here both the waveforms are related to an inverting comparator, but the first waveform is with respect to positive reference and the second waveform is with respect to negative reference. But the drawback of this comparator circuit is, if let me assume that some noise has been added on the signal, so here whenever the noise effect is going to be added, the noise is also considering it as an original signal, and as the noise levels are more than the reference voltage, there we are getting, instead of getting a 0 value, we'll be getting a 1 value. So it will manipulate the output. Instead of 0 we'll be getting 1, instead of 1 we'll be getting a 0. So this can be avoided just by adding some feedback path towards a comparator. So if we are adding a feedback path, then the circuit now will be used in closed loop configuration. So here if we are adding a feedback path, we are able to eliminate the noise effects, and such a circuit is called as a Schmitt trigger. So this is a diagram of a Schmitt trigger. So in case of a Schmitt trigger, the difference between the previous comparator circuit and this one is that in case of a comparator there is a no feedback path, but whereas in case of a Schmitt trigger we'll be having a feedback path, and depending upon these feedback value resistance values, here the output will be having two levels. That is, in the previous case we are having only one reference voltage, so that if noise is going to be added up on the signal, the output will be not a perfect one. So instead of using a single reference, here we'll be using two references, that is upper threshold and lower threshold. So if input is applied to the inverting terminal, the output is opposite. That is, feedback to the non-inverting is same as that of the polarity of the output. See, in this figure we are giving the input towards a negative terminal, but output is given towards a positive. So the circuit output, that is V naught, is equivalent to minus V in. The same minus is fed back towards a positive terminal of an op amp. So when input is slightly positive than V reference, output is driven into minus V saturation. Similarly, when input becomes more negative than minus V reference, it is driven into plus V saturation. So the output always varies with only two values, that is either plus V sat or minus V sat. So in order to calculate this plus V sat and minus V sat, here we are assuming that wherever the output is plus V sat, it is plus V reference is applied. Whenever output is minus V sat, we are having minus V reference. So when output is equivalent to plus V saturation, such a voltage is called as upper threshold voltage. When output equal to minus V sat, it is called as lower threshold. The difference between upper threshold and the lower threshold will give an hysteresis. So the hysteresis should be as minimum as possible. And if we want to calculate the upper threshold and lower threshold values, the formula for those upper threshold is plus V saturation into feedback resistance by total resistance, that is VUT equal to Vsat into R2 by R1 plus R2. Similarly, VLT lower threshold equal to V minus Vsat into R2 by R1 plus R2. We substitute these values of upper threshold and lower threshold in hysteresis, will be getting hysteresis H is equivalent to twice that of V saturation into R2 by R1 plus R2. If we observe the last figure of this circuit, that is when input is greater than the lower threshold, when input is greater than the lower threshold, output should go towards a negative value. That is the reason that the waveform is moving from positive value towards a negative value, and this will be repeated in a cyclic manner, and it will continue its path, and the arrows represents how it is moving, that is whether output is changing from plus to minus or minus to plus, depending upon whether it is inverting Schmitt trigger or a non-inverting Schmitt trigger. The other more important thing is Schmitt trigger is also called as a regenerative circuit because it is generating the same sort of waveform plus Vsat or minus Vsat repeatedly. So it is called as regenerative comparator or a regenerative circuit. And the other thing is it is also called as sine to square wave generator. So if input is a sine wave, the output will be a square wave for a Schmitt trigger, and we can avoid the disadvantage of comparator, that is even the noise is going to be added up on the signal. We can remove those noise signals because here in case of a Schmitt trigger we are having two threshold voltages, so that we can minimize the noise effects when compared to that of the comparator. These are the basic applications of an op amp.